So far we learned about energy level and the wave functions of hydrogen, right? So hydrogen atom is unique in the sense that it has only one electron, so we don't have to consider electron-electron coupling. Okay, so in that sense, we can really solve Schrödinger equation to get analytical solution, right? And with that, we got discretized energy levels, and then we saw how the wave function behaves, and how that one is translated to probability density function, right? And then from that probability density function, we kind of introduce, like electron cloud. Okay, so with that, we can actually try to understand other atoms with electron with a hydrogen model. Okay, because for other atoms, they have more than one electron, and we have to consider electron-electron coupling, which makes situation more complex. But we are gonna anyways try to use hydrogen model to kind of understand other atoms. Okay, so then obviously we cannot really ignore electron-electron coupling. So because of electron-electron coupling, when we consider like a sodium or mercury, which has more than one electron, obviously, now energy levels are shifting. Okay, so for example, for hydrogen, 3s and 3p were exactly at the same energy, right? Do you remember? Because energy levels of hydrogen depend on only n, right? The n value, quantum number n value, which determines this the first digit. Okay, but in this case, when we consider this sodium atomic number is 11. Okay, so in this case, when we consider like Schrödinger equation with approximation and numerical calculation, we can obtain this 3s and 3p energy level, and it turns out that 3s is lower and 3p is the next, and then as you see other energy levels, 4s, 3d, 4p, 5s have all different energy values. Okay. And then here, obviously, it's not showing, 1s and then 2s, 2p, okay? Because we are assuming that those are already filled, right? We have 11 electrons there, okay? So then 10 electrons will be, filled at lower energy levels, and then the 11th one is going to fill in actually 3s, right? That is essentially kind of how we filling the electrons in orbitals. And then we can consider also mercury here. So for mercury, mercury atomic number is 80. Okay, a lot of electrons. And again, because of electron-electron couplings, now we have different energy levels or different energy values for n is n equal to 6. For example, here 6s, 6p have different energies. And also, when we look at the 6p, even within 6p, it has actually varying energy levels. Okay, here. So I mean, these are all because of electron-electron coupling, and then that is how we should consider to fill the electrons in orbitals. Okay. And also, we can actually try to understand this, basically. The chemical behavior using these energy levels. Okay, so this one is kind of hard to see. Maybe you can kind of download the PDF and then take a look at it. But this is essentially like all the energy levels for like various atoms. Okay, so this one only has from hydrogen to silicon. Okay, so obviously like we are increasing number of electrons as we go like a larger x-axis. Okay, so then one thing you can notice here is basically as we increase the number of electron, for example, let's look at just 1s energy level kind of goes lower and lower and lower, right? And then that's the same case for all other energy levels. For example, 2s going kind of lower overall, and also 2p going lower. Okay, so here trend toward lower energy due to increased number of protons in nucleus, or number of electrons. Okay, and then now we are going to start filling the electrons in orbitals. Okay, so for hydrogen, obviously we have one electron that goes right into 1s, and then for helium we have 2 electrons, so 2 electrons will go into 1s because 1s has 2 parking spaces, right? 2 available spaces. And then now we are gonna start filling in 2s, because again here we are applying Pauli exclusion principle. And that states that one available parking spot can be filled with at most one electron, right? So either empty or filled with one electron. Okay, so this is why third electron cannot go to 1s, it has to go to 2s. Okay, so then we are gonna basically filling in 2s is filled, and then 2p has 6 available parking spaces, right? And then we are essentially kind of filling in, for the atomic number 10 niobium here, we are essentially filling 6. Okay, so then for this one we can actually try to understand chemical behavior, because like as we learned in chemistry class before, we learned that this group 18 is the most stable, right? This is essentially called like a noble gases. Okay, the reason for that is when we actually look into the energy diagram here, look at this one, helium, right? This is a group 2, and then here niobium here, group 10. If you look at it now, this energy is actually very low, right? Consider this one, and then this one is lower than any other ones, right? And also if you look at this atomic number 10 group, the highest filled band or highest filled orbital is actually located very low, right? So this is why it's actually very stable. Okay. And another thing you can notice is that basically for the periodic table, we learned that this group 2 and then this group 17 is very reactive, right? And then this one tends to lose the electron, this tends to fill the electron, right? Obtain the electron. Okay. The reason for that is, again, if we actually go to energy diagram here, for example, if you look at this lithium, okay, so now this 2s, electron sitting in 2s is relatively high, right? And then if you look at it, by losing this electron, it can actually go to this energy state, right? So this is why this lithium is actually very reactive. Okay, so and then by losing electron, it can actually go to much more stable form. Okay, this is why lithium has actually very high reaction rate. Okay. And also another thing is, for example, fluoride here, in this one, again, if you actually gain the electron, what does it mean? It can actually go to this kind of energy state, right? This is why, this one tries, kind of tend to obtain electron. Okay, so for example, here, this is a very reactive unfilled shell at low energy, and it's going to try to fill such that it goes to actual kind of state. Okay? So that this one generally applies even for here, like a sodium here, right? Sodium is now the electron is sitting in here. By losing this electron, it can actually go to this kind of energy state. So this is why like group 2 has a very high reaction, right? And then it's group 1 here, lithium, and then not sodium. Okay, this one tries to lose electron such that it actually kind of goes to kind of stable, stable energy state. Okay, yeah. So here, lithium and sodium. Okay, so this is how you can understand. Also, this one is also can be translated to this first ionization energy of the elements. Okay, so this ionization energy means energy required to eject electron. Okay. So for example, if you look at now this kind of helium and this niobium here. So for example, in this case, it takes a lot of energy, right? It's a kind of a peak. Okay, it takes a lot of energy to eject electron out of it, because this the helium, niobium, very stable, so it's kind of hard to take electron out. Okay, but if you look at now this lithium and sodium, right? It's kind of one of the lowest here, and then that one, it can very easily lose electron, right? Because by losing it, it can actually go to much more stable kind of energy state. So this is why, this one has a much smaller, like first ionization energy. Okay, so like this one and then this one is all related to kind of how energy orbitals form from electron-electron. Okay, so this is how we can understand like the chemical behaviors from periodic table. Okay, so again here we are essentially kind of using energy levels obtained from hydrogen, right? But here using some electron-electron coupling concept, we are kind of locating energy levels, and then from there we can even understand the chemical behavior. Okay. All right. Okay. So then the next one here is we talked about this Schrödinger equation for atoms, right? And then from hydrogen case, we obtained energy levels, right? Discretized energy levels. And then that one was just kind of theory, right? But, experimental actually showed that Schrödinger equation solution is actually accurate. Okay, so this is essentially kind of what I'm going to cover here. So for example, if we actually put in some like energized matter, energized atom in the container, and then it can actually emit photons. And then, using the spectrometer, you can analyze, like what kind of a frequency of that photon, is this, and also, we can analyze it. And it turns out, for example, this is an experimental result. Like for hydrogen and helium and mercury, it has all different kind of peaks of photons. Okay, so for example, here this is 700 nanometer, 400 nanometer. It has all different kind of the peak, and it turns out this peak is actually very unique in the sense that it really depends on the material element, and also the peak itself is actually very discrete. Okay, and then that one is kind of consistent with the Schrödinger equation result, and then that one can be understood by this kind of electron transitions. Okay, so again we are going to use a hydrogen case. Okay, so by solving Schrödinger equation, we obtained these energy values, right? Energy of hydrogen depends on only n values, right? And then n goes from 1 and n can be only integers. Okay, so with that, this is the actual energy level. Okay, n equals 1. This is a 0 electron volt, or you can think of this as a minus 13.6. Okay, so this one can be translated into basically minus 13.6 electron volt. And then this one, you can think of this as a 0 electron. Okay? We are just kind of taking different references. Okay? So with that, this is ground state, the lowest energy, and the next available energy is this one, right? And then it keeps going on, and then obviously when n is infinity, is essentially 0 electron volt, or if we take the ground state as a 0 electron volt, the maximum is a 13.6. Okay? So then, like when the electron is in the ground state, you can excite those electrons. And how do we do that? We basically, give some stimuli. Like for example, we collide with other atoms, or we illuminate ion atom. Okay? We are essentially injecting electrons into atoms such that electrons can gain some energy and jump into higher energy. Okay? So for that, there can be many cases. For example, if it's in the ground state, we can actually input, sufficient high energy. You can go to n equals 2 state. Okay, and also if we input a lot of energy, we can even ionize. The ionization means that we knock off electron completely out of the atom. Okay, so if we put larger than 13.6 electron volt, electron will be completely knocked off. Okay, but if we input, for example, larger than 10.2 eV, it has sufficient energy for electron to go from ground state to n equals 2 state. Okay, so that is essentially called absorption. Okay, and then when electron is in the excited states, it actually tries to minimize energy. So for example, if it's in the n equals 3 state, and then if it goes to ground state, it has to lose energy, right? And then that loss of energy is often released as light, okay, photon. Okay, so that is essentially kind of an emission process. Okay, so when electrons lose energy, like from n equals 3 to n equals 1 state, like the loss of energy is essentially converted to photon and it emits the light. Okay, so that is essentially energy transition process. And then if you look at it, this transition, it has to be jump, right? It's essentially called quantum jump because, again, energy is discrete, right? Energy is not continuous, energy is discretized. So what that means is that when this one goes from ground state to any other excited state, it has to gain sufficient energy to go to other states, right? And then this is essentially jumping, okay? Because it cannot go continuously, right? So in the sense, those energy transition can be evaluated by this, simple calculation, energy of initial state minus energy of final state. Then, using this energy value, we can just simply plug it in, and then we can kind of calculate that. And then this is kind of very similar to like an exam problem, right? But for that case, it was infinite potential well, but now this is about, hydrogen case, right? So then, this when a system transitions from an excited state to the ground state, it often releases energy in the form of a photon, and then we can evaluate what the frequency of that photon is, right? By basically using this energy transition. So, and then this is essentially the equation for that, and we can apply that to kind of evaluate what is the kind of frequency or wavelength of that energy transition. Okay? For example, if you look at it here, like between ground state and any other excited states, those energy difference, okay, here, these energy difference correspond to these wavelengths. Okay? And then also, if we just focus on the first excited state and any other, like excited states, wavelengths or frequency is corresponding to this. Okay? So then this Balmer series, okay, and then this is essentially called a different name. Okay, so for example, when we talk about just ground state, it's called the Riemann series. First excited state, Balmer series, and second excited state, Paschen series. Okay, like we just named it this way. So then if we look at just a kind of Balmer series, okay, that is essentially from excited electrons to the first excited state, okay, that is essentially when n equals 2, the lambda, okay, this energy difference corresponds to 656, 486, and so on, okay? And then, when we actually experimentally kind of test it, it turns out those spectrum, okay, using the spectrometer, the peak we can obtain is essentially kind of this is essentially kind of experimental results, and then this is a theoretical results that is expected from solving Schrödinger equation. And it turns out theoretical results and experimental results were exactly matched. Okay, so what does it mean? Like actually Schrödinger equation is actually accurate in describing hydrogen, and this one strongly proves that the energy levels of hydrogen is discrete, right? And that follows exactly this description, right? Energy description. Okay. And also another thing you can notice was that, this is a kind of a, it's beautiful in that this wavelength is actually very unique, right? For example, if you get like 410, then you exactly know how that transition happened. Okay, so for example, if you get 656, okay, if you identify 656, that means energy transition happened from this level 3 to level 2. Okay? So this is how you can identify, the details of energy transition for every element. Okay? So this is why spectrometer is actually a very powerful technique to identify, chemical reaction and, these energy transitions. Okay? So, and then there is a kind of a one specific rule for this energy transition. Okay, I mean, I'm not going to go into details, but the transition, the energy transition must follow these selection rules. Okay, that means this delta L must be, plus minus 1, and also this delta M, okay, M quantum number difference should be 0 or plus minus 1. So what that means is that, I mean, M is kind of hard to see in this description, but L is easy because L is related to SPDF, right? That orbital. Yes, in that sense, when we make an energy transition, okay, when electrons go from one state, one energy state to another state, it has to be just kind of one change element, right? From S that is equal to L is 1, L is 0, L is 1, L is 2, L is 3, right? So for that, like when electron go from here to here, right? So that one is still following the selection rule because delta L is just 1. But, for example, when electron is here, electron cannot go from here to here, okay? Because that is delta L is 2. Okay? So there is a certain selection rule that you need to follow to make energy transition. But as long as you make that, electron can jump from one state to another, freely. Okay? So that is the hydrogen atom and other atoms energy transition. So now we are gonna get into kind of new topic, which is called kind of band theory. But before we get in there, do you have any questions about this energy transition? Yeah. Yes.
4S go to 3D, for example. Like, I know, so 3P and 3D, for example,
Yeah.
those are only marginally different as far as energy levels go. The 3D is still slightly higher.
Yeah, 3D is slightly higher for this particular case. This is a lithium energy level diagram.
Right, so why would 4S skip it and go to 3P?
Say it again, like 4S, why 4S?
Like if we were dropping an electron, I mean, I'm just looking at the arrows, right? So like,
Yeah.
there's not another that goes from 4S to 3D.
Right.
It skips it.
Yes. So this is essentially kind of possible scenarios, right? So for example, electrons, we are essentially satisfying these selection rules. Okay, so for example, you cannot go from 4S to 3S because selection states that delta L must be plus minus 1. So for example, 3S to 4S, that is like L is still 0, right? So it's kind of telling you just the possible scenarios with here. That is essentially just following this delta L plus minus 1 and delta M 0 and plus minus 1. Yeah. Thank you. And any other questions? So if not, we can actually get into band theory. Okay, so this one is going to tell us, we are going to basically focus on explaining how electrons behave in solid. Okay, so far we really look at kind of an individual atom, right? But like a real matter, like the large scale object is made of like millions of atoms, right? So then we will try to understand how electrons behave in solids. Okay. So and then this one is crucial concept because we can understand conductor, semiconductors, and insulator behavior. Okay, with this band theory, and also this is essentially kind of expanding ideas of discrete energy levels to crystal. Okay, and then we are going to talk about energy band, and also with that we are going to talk about some of the applications. Okay, and then using this band theory concept. So let me just kind of quickly recap, how a hydrogen atom behaves. Okay, so now we are again emphasizing atom. Okay, for individual atom, we can obtain this wave function, right, by solving Schrödinger equation, and this wave function has this radial component as well as this angle dependent, right? That is called the spherical wave function, and then we cover that, so there are 4 quantum numbers. So that is 3 quantum number is an N, L, M, and 4th quantum number is a spin, right? And for the simplest case, when N is 1, L is 0, and M is 0, the solution is given as this. And then here there is a constant A. Constant A is a 0.529 angstrom, that is called the Bohr radius. And then, as we just kind of discussed, for hydrogen we have discrete energy levels. Okay, here again this is minus 13.6 eV and then 0 eV here. And this is the some examples of radial wave functions. Okay, so this is corresponding to 1s, and then this is corresponding to 2s and 2p. And with that, we can consider probability density function. You guys all know that now. This probability density function, again, that is basically probability of finding the matter at x. And then when we integrate probability density function, this must be 1, right? This is called the normalization. And then for 3D case, this probability density function description changes a little bit. Now it has r square, okay, because we are talking about 3D case. So then when we consider normalization, it has to be negative infinity to infinity, and the r square goes in here, and then psi star to psi, and then we consider this psi zeta, this at infinity. Okay? And then with that, for hydrogen atom, if we obtain probability density function in radial direction, okay, so then that is essentially kind of a, this is what we get for 1s, 2s, and 2p, right? And then this is essentially the probability of finding the electrons staying at 1s orbital, and then this is a probability distribution of electrons sitting at 2s orbital, and then again this is at 2p. Okay. So this is what we already learned, and now we are gonna try to construct crystal. Okay. So we were really focusing on just individual atom, but now we are gonna construct crystals. Okay. So what that means is that we have to now bring atoms together, right? I mean, in order to build a crystal, you have to, bring many atoms together, right? So the way we are gonna do here is, this is a probability density function of an isolated hydrogen atom or single atom, and now we are bringing 2 atoms close to each other. Okay, so in this case, basically, this is a 1 hydrogen atom, and then another hydrogen atom, and then we are kind of bringing close to each other, right? So then this is a probability density function for this hydrogen, and then this probability density function for another hydrogen, right? Then when we bring these 2 atoms together, now the electron from one hydrogen and another electron from another hydrogen, these 2 electrons start interacting with each other, right? Before, when it was isolated, there was just a single isolated electron. But when we bring 2 hydrogen close to each other, now 2 electrons start interacting with each other. Okay, and then what that does is, it actually creates discretized energy split. Okay, so before, when it was isolated, we had the single energy, right? But when we bring these 2 atoms close to each other, now this energy level is split into 2. Okay, again, that is because of electron-electron interactions. Okay, so this interaction, okay, electron-electron interaction results in discrete quantized energy levels splitting into 2 discrete energy levels. Yeah. So then, what happens when we bring many more atoms, right? So for example, now we are bringing more atoms close to each other. So what happens is essentially, when it's far away, okay, when it was far away, those are essentially kind of isolated. Okay? When it was in isolated state, it has just kind of an energy level, like that we obtain from Schrödinger equation. Okay? It doesn't do anything because there is no interactions, right? But as we bring atoms close to each other, at some point there is electron-electron interactions happening, and those electron-electron interactions are creating energy split. Okay? So then, as we bring closer, now the energy splitting happens, and then there will be some kind of a, like this energy kind of band that is formed. Okay? So what that means is that, like this one is essentially considered as, like n equals 1. But, like we have actually other energy levels as well, right? For hydrogen, we have n equals 2 energy level, n equals 3 energy level. And overall, this one is kind of a, like located kind of far, right? And then as we bring close to each other, this higher energy state start interacting first, and then it's kind of showing the energy level split. And then the next lower energy is kind of getting interacted with each other, and energy splitting happens, and n equals 1. This is essentially kind of, like a later, or like a much closer distance energy splitting starts happening. Okay. So that is essentially kind of a the energy splitting. So here, now let us kind of consider this sodium case. Okay, sodium atomic number is 11, or 11 electrons. Okay, so for this one, like obviously the farthest out, or like the highest energy level that electron is occupying is 3s1. Okay, so if we bring two atoms close to each other, now when it's far away, again it's just kind of single energy level. But when we bring two atoms close to each other, now energy is splitting, and like that, and then there will be some kind of equilibrium position. Okay, so there will be equilibrium position here. But anyways, like if we bring 4 atoms, now 4 energy is split. Okay, and then if we bring many atoms, like millions of atoms, then within this kind of a defined line, there will be like millions of lines, millions of energy split. Okay. So again, here, like this is what it kind of tells you: energy level splits into a band of energies when atoms are brought together. If a million atoms are brought together, each individual level splits into million new levels. Okay, within this band. Okay. So then think about this way. Okay. So now we have like a million energy splitting within this defined, or within this shaded area. Technically, the energy difference is very, very small. And then what that kind of suggests is that the energy level within this shaded area is kind of a quasi-continuous. Okay? Because there are million energy levels within this defined area, and then energy difference is so small, we consider that as kind of practically continuous energy within this band. Okay? And then this is essentially kind of what we call energy band. Okay, so energy levels are discrete but closely spaced. Energy difference is extremely small. So for all practical purpose, we have a quasi-continuous energy distribution within this shaded area, and then this is called energy band. Okay, so this is a crucial concept for electrical conduction. Okay, for any solid material. And probably some of you guys heard about energy band. Have you guys heard about that? Energy band? Band theory? Okay, yes. So this is essentially kind of an energy band, okay? And then, again, this concept comes from discretized energy level from individual atom. But when we construct crystal, okay, as we bring many atoms close to each other, now this energy splitting happens, and that energy splitting creates this energy band, okay? So with that, let us again visually demonstrate here. So for individual atom, we have discretized energy level, right? The kind of fixed energy, and then for 1s we have 2 parking space, 2s 2 parking spaces, and 2p 6 parking spaces, and 3s has 2 parking spaces, right? And then we have 11 electrons. So let's kind of try to fill those electrons in orbitals, right? And then 2 will be filled, 1s, 2s, and then 2p6, and then last one will go into 3s, right? But what about crystals now? Again, when we bring many atoms close to each other, this one will be splitting, right? And then we are essentially forming the band, and then here we have, let's say, let's just, for simplicity, let me just assume that this one has 10 atoms. Yeah, obviously, for real crystal, it's gonna have, millions and billions of atoms. Yeah, but just for simplicity, I'm just kind of saying that this one, let's say this one has 10 atoms. Yeah. So what that means is that, for 1s band, we have how many available space there? We have 10 times 2 available spaces, right? Because each individual atom has 2 parking spaces, right? Each individual atom. But we have 10 atoms, and then those 10 atoms, or 10 atoms are brought close enough, then it's gonna get into energy splitting, right? And then it's gonna form the band, but within that we have 20 states there. Okay, 20 states. So then we can kind of continue on that. Now that is essentially 2s. We also have 20 available spaces, and then 2p we have 60 available spaces, right? So in this case, think about it, crystal. For 10 atoms, how many electrons are there total? We have total 110 electrons, right? We are essentially filling those 110 electrons in this energy band diagram. So here, obviously 20 goes here, right? And then 20 goes here, and 60 goes here. Now, 100 are filled. Then we have 10 left, right? And then those 10 will go into now 3s. But how many spaces are there here? We have also 20, right? So out of 20 spaces, we are filling 10. So we are essentially kind of drawing only half of them. Okay? This is essentially called half-filled energy band. Here, all of them are completely filled, but this one half-filled. Okay? So this is essentially kind of how we can understand this energy band. Okay? And then this is a individual atom picture, but this is the crystal picture. Yeah? Because as we build the crystal, energy splitting happens, that forms the energy band. And then here, this is essentially quasi-continuous energy. Okay? So it's kind of really packed with each other. Okay? But obviously, when you look at it, this energy band, there is a gap, right? There is some kind of appreciable value here, the gap. Okay? So within the band is continuous, but between band there is a gap. Okay? So that one is that's something I want to make a note. And then this one is kind of easy to understand, but let us now look into silicon. Okay? Because silicon is the kind of core material in semiconductor, right? And then this silicon is behaving kind of in a kind of funky way. So let us kind of look at this one. Okay? So silicon, if you look at it, this one has 14 electrons. Okay? And then if we normally work at a kind of an individual atom level, 3s2 and 3p2. Okay? So what that means is that, at 3s, we are filling 2 electrons, and then 3s is completely filled. So 2 last two electrons should go into 3p level, okay? Because 3p level is a higher energy than 3s, okay? And then now we are going to construct crystal. Okay, as we form the crystals, it's actually kind of very hard to see. You guys should. This PowerPoint is has been uploaded on Sakai. Okay, so you guys should download. There is actually some warning you cannot really see, but here. Okay, so this is essentially kind of far away, isolated condition. Now 3s is at the lower energy than 3p. Okay, so for example, here this is essentially 3s and then 3p. Okay, this energy. So when it's isolated, but when we bring the silicon atoms close to each other, again, now energy splitting happens, right? Because electron is interacting with each other. So then, if we bring actually further, okay, now energy splitting happens, and then now these 3s and 3p energy bands are mixed with each other right here. Okay? And then if we bring electron even closer at a kind of equilibrium position, what happens here is that now there is actually lower band, okay, and then higher band. But here, lower band has 4 available states. Okay, 4 n states for the lower band, and the higher energy band has 4n states. This one is kind of very interesting in that 3s, it has how many available space there? 2, right? What about 3p? 6, right? But now when we build crystal, okay, then this energy splitting is kind of happening in a kind of weird way, such that now it's forming lower band, higher band, and then this lower band has 4 orbital spaces, and higher band has 4 orbital spaces. Okay? So this one is actually called like a hybridizations. Okay? So this is called like SP hybridization. Okay? And then that's kind of creating new energy band. Very different from individual atom picture. Okay? So here, at the equilibrium interatomic distance, the band is split. So 4 quantum states per atom are in the lower band, and 4 quantum states per atom are in the upper band. Okay? So what does it mean? We had 4 electrons, right? We had 4 electrons. So if we construct crystal, now all those 4 electrons will be sitting in lower band, right? When we build crystals. Okay, so at absolute 0 degrees, electrons start feeling the lowest energy, and because we have 4 electrons available per atom, all those electrons will sit in this lower. Okay, and then you kind of notice that like between lower band and higher band, there is energy gap here. Okay, this is essentially. There is an energy gap, EG there, right? So this is essentially called band gap. Okay, have you guys heard about band gap as well? Okay, so this band gap is actually very important material parameter for charge transport. So there's a band gap is the width of the forbidden energy band, the size of this energy difference. Okay, so for this one, let us now kind of work on this individual atom picture and the crystal picture again. Okay, so again, let us look at this one. We have, the 2 available spots for 1s, 2 for 2s, 6 for 2p, 2 for 3s, and 6 for 3p. Right? This is an individual atom picture. And then if we start filling the electron in orbitals, obviously, like 2 filled, 2, 10 filled. And then we have 4 available electrons, and then 2 will go into lower energy, right? 3s is filled, and then 2 will fill in 3p. But if we construct crystal, and then because of this sp hybridization, we are forming lower band, lower sp band and higher sp band, right? And then that is essentially, like we are filling all those electrons in lower sp band, because it has available 4 n states and 4 n states here, because we had a 4 per atom, right? And then those ones will fill in this lower sp band, yeah? And then we are essentially creating that. So then in the sense, if you look at it, individual atom picture and crystal picture very different, right? Individual atom will fill in is 3p, but for crystal, because of hybridization, all those electrons will fill in lower sp band. Okay? So, and then now a low sp band completely filled and a high sp band is completely empty, and then the energy difference between this high sp band and low sp band is called band gap. Okay? So that is essentially kind of the concept, and then this band gap is very important to determine whether the material is insulator or conductor or semiconductor. But that part we are gonna continue to discuss tomorrow. Okay, so that's it for today.